right, students, welcome to the first part of section 3.4. We're going to be in this section just talking about a lot of physics actually and how the derivative relates to motion. So the idea in this is going to be one-dimensional motion. So what we have is we have a position of an object represented by s of t. And what this is showing you right here, what this diagram shows, is a change. So this right here is just saying a change in position when you're subtracting two things like this. Okay, S of t is what we're going to use to represent that displacement. So when you see delta S, that means change in position. And the time is just you're adding a time interval to that. So this part right here, when it says F of a plus delta t, that just means at a later time, that's what the position is. And you're looking at the difference between two positions at two different points in time, and that gives you what's called the displacement. So this is your position function. First thing that we'll take a look at is the average rate of change. And I think we've talked about that a little bit. I'm going to open up this applet. And this relates well, of course, to what we've been talking about with a derivative. We started off by talking about secant lines, so an average rate of change would just end up being the slope between two points on this curve here. You can think of this as time. This would be like 2 seconds. That would be 4 seconds. So this object has moved, and these are its displacements. So the y-axis here is given how far this object is from the beginning. This would be the beginning point here. For instance, right now at 2 seconds, then that position is maybe it's a meter away from its original position, like that. So the average rate of change from 2 to 4 would be nothing more than just the slope of this secant line. So you'd have to take these 2 points, you'd have to take this point 4,2 and this point 2,1 and calculate its slope. And it's rise over run, and you can usually manipulate this a little bit on these applets. I don't know if you can on this one very good or not. Okay, there we go. Okay, so let's see. So as I'm changing my position, that average rate of change is also changing, okay, because it's a slope of a line, and you can kind of see how this thing is calculating out and so forth. All right, so that's the idea. Now what we kind of will eventually get into in this section is when those 2 points get real close together, then that approximates the instantaneous rate of change, which would be the rate that you're traveling at a particular instant in time. Okay, so kind of going down here, this is kind of what we've been talking about so far. The slope of a tangent line gives an instantaneous velocity. The secant lines, when you find the slope of a secant line, you're getting a average velocity, okay? Average rate of change. So if we look down at this definition right here, this is really what this is doing is this is just finding a slope of a secant line. And what we have here is this numerator right here is a change in position. Okay, so you're measuring how your position changes. And then this delta t, that is a change in time. All right, so that's what it is. Just like slope is rise over run, you can think of slope as change in y over change of x. Well, in this case, the function is the change in position, and then delta t is the time. All right, so that's the idea. And then instantaneous velocity, well, if you look at the two things here, it's the same expression here, except what you're doing is you're doing the limit as delta t goes to 0. So you're actually doing a derivative. You recognize this as coming from the definition of a derivative. So the velocity is really just the derivative, the first derivative of the position function. Okay, so that's what that is. And the idea, we've talked about that, and I'm going to show you one thing on this applet here. Let me open this up for a second here. This is Desmos, another really good applet generating thing that you can manipulate. So see, right now this is a average velocity because we're finding the slope of a secant line. And the idea on this is right now h is 3.6. Okay, so I'm moving from 2 out 3.6 units. So the idea, if you watch this, I'm going to take this slider kind of like this, and h is getting smaller. So as h gets smaller, then this is getting closer to a tangent line. So as that gets closer and closer and closer to 0, it gets close to the instantaneous velocity. So theoretically, if we let the limit go to 0, h go to 0, then we get the instantaneous velocity. So this is an average velocity when you got 2 points. Close it in, do the limit as h goes to 0. Now you've got an instantaneous velocity. And it's that same expression, change in position over change in time. Okay, so that's how that works out. Okay, now, so let's go ahead, let's look at some examples here for a few minutes. All right, so what this figure says is this is a position of an airliner on an out and back trip from Seattle to Minneapolis. S equals f of t is the number of ground miles from Seattle, t hours after 6 a.m. So right here would be the takeoff point at 6 a.m. like that, okay? And what's happening on this is, okay, this, like for instance, at 1 hour, the displacement is, that looks like maybe about, I don't know, maybe 300 miles away. After 2 hours, it looks like that's maybe 1,000 miles away and so forth. At 4 hours, you are 1,500 miles away and so forth, all right? And then notice as you get further out here, when you get to 8 hours, well, we're only maybe 100 miles away. So you want to think about what this means in the context of the problem with this, this airliner then. So first thing we're going to do is calculate the average velocity during the first 1.5 hours of the trip. Okay, so what we're going to do is we need to find 2 points. So this would be 1.5 hours right there. So let's just go up to 1.5 and estimate where that is. So that point looks like it's 1.5, and that would be 600 miles. And then, of course, the first point right here would be 0, 0. So if we want to find the average rate of change, I'm just going to abbreviate that AROC, then really what we're doing is we're just doing the slope of that secant line that goes through those 2 points. So you can think of a secant line crossing through those 2 points like that then. So what you need to go ahead and do is you just need to go ahead and do the slope of that secant line, and then that'll give you the average velocity over that time period. Okay, so we would have the change in position. So this is changed from the starting point to 600 miles away, and the time interval is changed from 1.5 hours to the beginning. So you would have 600 over 1.5, and then you can simply calculate that out then. All right, let me get my calculator. Okay, man, like magic, up pops my calculator. So 600 divided by 1.5, this would give you the average rate of change. So that would be 400. Okay, so that average velocity would be 400, and this is in miles per hour. Okay, it's important that you always write the units on here. That's real important. It's a rate of change. It's the change in position, miles, over the change in time, which is represented in hours. Okay, so that means on that time interval, the plane is traveling at that average velocity of 400 miles per hour. Okay, its velocity's changing. I mean, sometimes it's going, just 100 miles an hour when it's, getting ready to take off, and then it's increasing its speed. Okay, the next thing we're going to do is calculate the average velocity from 130 to 230. Okay, so I'm going to erase what I've got here. And remember, we start at 6 a.m. here, so this would be, if you go, just kind of count this out, 7, 8, 9, 10, 11, 12. This would be 130 right there, it looks like. And then 230 would be, it looks like, right in here. Okay, so I think I got that okay. All right, so what we're going to do, again, is we're just going to look at a couple of points then on that, okay? Okay, so it looks like here, we'll just estimate this point, that looks like, and we would use 7.5 hours later, and then that looks like 300 miles away from the airport. Okay, and then this right here looks like 8.5 hours later. That's what 2:30 is, and looks like they're at 0. Okay, so that means something. So again, what we do is we do the average rate of change. So when we do the average rate of change, what we're really essentially doing is a slope of a secant line. So I'm just going to subtract these, and it doesn't matter what order you subtract these in. I'm going to go 300 minus 0, but if I choose to do the change in y that way, the change in position that way, then I got to do the change in time the same way. So if I do this, I get 300 over negative 1, so I get negative 300 miles per hour. Okay? Well, you may not be familiar with a negative, but velocity can be negative. Okay, what do you think that means if the velocity is negative? Yeah, it has to do with position. Okay, so see, this is kind of going in the positive direction. So this is going away from the airport. This is actually returning to the airport. Okay, so that's what that means. All right, and I think that's what the question is on the next thing is we're going to look at when the velocity is equal to 0. Okay, so that's how you find average velocity. All right, now what we're going to end up doing on this is when is the velocity 0? Well, that would be where there's no change in position over time. So what do you think the velocity would be 0? And remember, velocity is nothing more than a slope of a tangent line. Right now we have a positive sloping tangent line. Right now you've got a positive sloping tangent line. But the question is, what's happening here? All right, that's the thing. You have a horizontal tangent line with a slope of 0. So what it looks like on this problem is between 3 and 5 hours, the velocity is 0. Okay, so what we're going to say on that would be 6 a.m. This would be 9 a.m. because it's 3 hours later. So between 9 a.m. and then this would be 11 a.m. The velocity would be equal to 0. What does that mean? Well, it means the plane landed, okay, number one. So what's happening? It's at the airport. So it's at the airport terminal, and I guess it's waiting for its return flight. Okay, so it's at the airport terminal at rest. That's what that means. Okay, I like this problem because it's easy to picture, I think, in your head, and how you can graphically represent change in position over change in time. Okay, so now it says what is the velocity at noon, and explain why it's negative. So I'm going to erase some of the scribbling I did on here, just kind of get rid of some of this stuff. Okay, and if we look in here, that would be 6 hours later, right? So that would be noon right there. So if we go up to that point right here, we end up having this. Well, let's determine the velocity at this then. So what we're going to do is, it's a slope of a tangent line. Now we have to estimate this tangent line. So let me kind of show you what my thought process is. To me, I need to find 2 points because I'm not given the function, so I can't do the derivative, but I can estimate. And to me, if I use this point, that's a pretty good approximation of the slope of that tangent line at noon. So what I'm going to do is I'm going to just do that. So this first point right here is 6 hours later and a position of 1,200 miles from the airport. And then the second point right here is 7 hours later, and that position is 600. So we're going to approximate the velocity. Okay, we're going to find the slope of a secant line, but the reason I chose that point, number one, it's a good point with whole numbers, and it just looks like looks to me like the tangent line's pretty constant, has a pretty constant slope there, which you kind of expect from an airline. It's going to have a fairly constant rate of change once it gets its speed. So what we'll do on this then is we just do the slope. So we're going to do 1,200 minus 600 over, and then we'll do this, 6 minus 7. So that would be 600 over negative 1. So that would be negative 600 miles per hour. Okay, now the question is, what does it mean if it's negative? Well, we already talked about that. That just means it's going in the negative direction. The reason it's negative is it's just basically going back to the airport. Okay, so it's going back to its original takeoff point. Okay, so that's what's going on that. That's why it's negative. All right, so velocity can be positive or negative. Okay, so what I'm going to have you do is I want you to look at this problem and pause the video and see what you come up with on this. These are good problems to give students to start with because it'll kind of get you to think a little bit the right way about how position changes over time. Okay, so let's go ahead and see kind of what we came up with here. And I'll run through this. So again, what this problem is saying is the patrol station is where you start. So that's your that's the station right there. Okay, and the first thing you're doing, the average velocity over the first 45 minutes. Well, let's see. So 9 a.m. is when this starts, and then that'd be 9:30 right there. This would be 10 a.m. So that's at 0.75. And if you look at this, you have the point 0.7530, and you're comparing that to 0, 0. So what I'm doing on that is I'm just doing the slope between these 2 points right here. So that's 30 minus 0 over 0.75 minus 0, so that's 40 miles per hour would be the average velocity of the car, okay? All right, so let's see. Right here, the next problem says from 0.25 to 0.75. So if I go over to 0.25, it looks like you have displaced 10 miles from the station now. So I got that point. At 0.75, which would be 45 minutes after at 9:45, that looks like that's displacement of 30 miles. So again, I just do the slope between these 2 points. So 10 minus 30 over 0.25 minus 0.25, or that 0.75, that would give 40 miles per hour also. And then this says, is this a good estimate of the velocity? Yes, it is. And the reason it is because if you connected those 2 dots, you could the instantaneous velocity looks like it would be the slope of the tangent line, and that looks like the slope of the tangent line is pretty much always about the same roughly in that time interval. So that's a really good estimate, I would say. Okay, the next one says on this interval, so at 1.75, the displacement is 15 north of the station. Okay, and at 2.25, you would be 15 miles south of the station. So you have these 2 points. So I just did 15, subtract negative 15, 1.75 minus 2.25. So I got negative 60 miles per hour. Okay, and notice on this too that, you know, this was 40, that's negative 60. This is faster. And can you tell? Well, it looks to me like it's steeper. This looks like it would have a steeper line than this does. So it looks like it's picking up speed at that particular point in time, okay? And what that means is you're going south, okay? So the patrol car is going south. Now this last problem I just sort of estimated it. It looked like, and I kind of look at it like here. From here to here, you're going north. All right, and that looked to me like around an hour later. It's probably a little bit more than an hour later. So I said from 9 a.m. to around 10 a.m., then we're going north. At that point in time, the patrol car is going to change direction. Okay, so it just does a little donut in the road. Or is that what you call that, a donut in the road when you turn around? Well, maybe he stopped at the donut shop real quick and got a donut. Okay, then he started going south, back towards the station, okay, like this. So I said from about 10 a.m. to about 11:45-ish, okay? So that right here, this would be 10, that would be 11, that would be 12. This would be 11:30. So to me, it was around 11:45-ish. You're going south, okay? Then he, you know, does a donut in the road and then heads back north towards the station for the rest of the time. So that's what I wanted you to see, just kind of estimating those times. You can't nail any of that down perfectly on that. So it's just kind of going north, going south, going north again like that. Okay? All right. So let's move to the next page. And we'll start getting into some definitions here and some calculus. Okay, so now we kind of get into the calculus here. So again, if we have a position function s of t, then the velocity is the first derivative. It's a rate of change, okay? So that would be the first derivative. The speed is always positive, so it's the absolute value. Okay, it's a positive number. See, when you drive in your car, you're always, your speedometer is measuring your speed, not your velocity. So speed is just the absolute value of velocity. And then acceleration is a rate of change. What it is it's a rate of change of velocity. So your acceleration is a measurement of how your velocity is changing. So it's another derivative. So we haven't really seen this yet, but if you see s double prime of t, that means what we call the second derivative, and it just means you do the derivative 2 times. And that's what we're going to do on that then. So once you get the velocity by the first derivative, you do the derivative again to find the acceleration. A couple of points on here that I wrote down. The velocity is a rate of change in position. Velocity can be positive, negative, or 0. The units are distance over time. Meters per second is a good example. The speed is the absolute value of velocity, so the speed is always positive or 0, could be 0. And the units would be, again, distance over time. And then the acceleration is the rate of change of velocity. And acceleration can be positive, negative, or 0 also. Positive would mean that you're probably speeding up. And negative would be you're slowing down. Okay, that's what that means. And then its units are in distance over time squared, so something like meters per second squared. A well-known constant is 9.8 meters per second squared. That is the gravitational constant on Earth. So if you drop an object, from a height, if you're neglecting air resistance, then it's going to accelerate at 9.8 meters per second squared. Okay. All right, so let's see. These are just a couple of diagrams here, and I want you to think about this a little bit. If this is position, then the velocity would be the derivative of this. The derivative is 2t minus 5. So that would be this line right here. Okay. And then the acceleration would be the derivative of 2t minus 5. The derivative of 2t minus 5 is 2. So that would be that. So this is kind of a way to look at this real specifically. Here's your position function. This is what your velocity function would look like, and that's your acceleration. Now, what this would mean is you have a constant acceleration. So that's going to end up being constant on that. And I want you to sort of look at this diagram and think of how this relates to derivatives. Right now, the slope of the tangent line in here is negative. The slope of the tangent line right there is 0. Okay, so see, we got the derivative, the velocity is 0 at 2.5. See how that matches? And then what happens is your velocity becomes positive because you have a positive sloping tangent line. Well, these are positive values. So you have negative derivative values. So notice the line is below the x-axis. And then you have positive sloping tangent lines. So notice the value of the derivatives above. And that's how that goes then, all right? And the rate of change of this is constant. So acceleration is how velocities change. Velocity is not changing on this at all, okay? It's always the same. Okay, it's constant because it's a line. Okay, so, excuse me, let's see. I said that wrong. The velocity is changing. What I meant to say was the acceleration's not changing. That's what's constant. Okay, all right, let's move to the next page, and we'll start crunching out the calculus a little bit here. So this problem says, suppose a stone is thrown vertically upward from the edge of a cliff on Mars with an initial velocity of 64 feet per second from a height of 192 feet above the ground. The acceleration due to gravity on Mars is about 32 feet per second squared. On Earth, it's 32 feet per second squared. So the acceleration, gravity is less on Mars. I think it's around a third of the gravity of the Earth. And here's your position function. Now, you don't have to worry about these numbers. When you take physics, you'll learn about a projectile motion equation. This turns out to be the height, and then this number right here turns out to be the initial velocity. So we don't really cover that formula in this calculus class. So we're going to determine the velocity of the stone after t seconds. Well, all you do to do the velocity is you do the first derivative of the position function. So go ahead and do that. That's going to be negative 6t plus 64. Okay, so that is your velocity function, which in this case is linear. Then it says at what time does the stone reach its highest point? Well, what's going to happen on this problem, if you graphed this on your calculator, and we'll do this in just a minute, you would end up having a parabola going upside down, kind of like that. Well, what happens when it reaches its height is that velocity, remember the velocity is a slope of the tangent line, okay, so that slope is 0, okay? So basically, at what time does the stone reach its highest point? Well, first of all, it happens when the velocity is 0. Because think about what's going to happen. For that instant in time, the stone is not traveling, it's traveling at 0, then it starts picking up speed as it goes towards Mars. So what we do on this problem then is you want to take the velocity, which is represented by negative 12t plus 64, and then you set that equal to 0. And then you want to solve this equation. So what you would get from here, negative 12t equals negative 64. Just subtract 64 from both sides, go ahead and divide by 12, and that would give you the time when that happens then. Okay, so this will give you the time, it looks like, in seconds on this problem. So 64 divided by 12 is going to end up being about, we'll just round that off to about 5.3 seconds. All right, so that would be the answer to that approximately then. All right, so that's how you figure that out with calculus methods then. So we now know how long it's going to take based on that position function for it to reach its height. Okay, the next question is, what is the height of the stone at its highest point? Well, the highest point happened at 5.3 seconds. So what that means we need to do is we need to do s of 5.3. All right, because remember, the position function gives you the height of the object. So we figured out that it took this long, 5.3, to reach its highest point. So just plug into the function. So you'll have negative 6 times 5.3 to the second plus 64 times 5.3 plus 192. Okay, now when I put this in calculator, I'm just going to put more decimals in for a little bit greater accuracy on that. You don't necessarily have to do that. So I'm going to go negative 6 times 5.3. I'll just put several decimals in there like that. And then plus 64 times 5.3. You can put several decimals. You could actually put the fraction in there too. You could put 64 over 12 and it would be precise. And then plus 192. And then that gives this then. Okay? So what I was saying is when we work this out, this is 64 over 12, and you could reduce that fraction. So 64 over 12, if you go through and do that on the calculator, and then go math fraction, that reduces that to 16/3. So you could do this like this. You could just go negative 6 times 16/3 to the second, and then plus 64 times 16/3. And then plus 192. Okay, you can either round or you can do it this way, okay, for the precision. Okay, and it's not much different, okay. So what you end up getting is, we'll say, 362.7 approximately feet above the ground. Okay, so that's our approximation of our maximum height. Okay, all right, so we got that. Now the next question it says is, when does the stone strike the ground? Okay, well, remember this is a parabola that's, upside down. So what's going to happen on this problem, and when we do this on the graphing calculator in a minute, is what's going to happen here is, what's the deal here? The stone strikes the ground when the height is what? Right, okay, the height is 0. Okay, that's when you know you're going to strike the ground. So it says, when does the stone strike the ground? It's going to happen when s of t equals 0. So we're going to have a mathematical equation we can solve then. So we're going to have this. We're going to have negative 6t squared plus 64t plus 192 is equal to 0. So if we can solve that quadratic equation, then we can figure out the answer to that problem. So this is a quadratic equation. We could go directly to the quadratic formula, or we could attempt to factor this. It's kind of up to us. I think all of these numbers certainly divide by 2. So what I'm going to do on this, and you can do this, you can go through and just divide everything by 2. I don't think everything divides by anything else. I think it's just 2 is as far down as you can reduce this. So if you do this, then we would end up having negative 3t to the second plus 32t. And this, I think I'll probably just go straight to the quadratic formula on that. And you can always do that just if you want to. So that's plus 96. And that's equal to 0. Okay, so you don't have to reduce that if you don't want to. You could also factor a 2 out of there, and if you factored a 2 out of there, you would just have negative 3t squared plus 32t plus 96 equals 0. Then you could divide by 2. I mean, you can do that either way. Okay, so what I'm going to do is we're just going to go straight to the quadratic formula. It may factor. You could certainly try if you wanted to. On these problems, to me, unless it's real obvious what the factoring is, I just go to the quadratic formula. So we have a is negative 3, b is 32, c is 96, and remember your quadratic formula in this case would be t is our variable is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. That is such an important formula that, I'm never going to give you the quadratic formula because it's so important. It shows up so much. That's something you really, really need to know. Okay? So this is negative 32 plus or minus the square root of 32 squared minus 4 times negative 3 times 96. And then all over 2a, so that would be 2 times negative 3. Okay, and we're going to do this with the calculator. All right, so I'm going to work out what's under the radical. We call that the discriminant. So I do 32 to the second. See, this is a plus. There's 2 negatives there, so it's plus 12 times 96. Kind of do a few things in my head. And then I'll record that. So now I've got negative 32 plus or minus the square root of 2176 all over negative 6. Okay. Then let me see what the square root of that is. If the square root turns out to be a whole number, then that means this thing could have factored. So let's see what it is. It didn't factor. So see, most time you just do that. Okay, just go to the quadratic formula. So we're going to do 2 things. We're going to do actually take this in 2 directions. We'll do negative 32 plus 2176 over negative 6, and we'll do that whole thing on the calculator. Then we'll do negative 32 minus square root of 2176 all over negative 6. One answer will make sense, the other one will be nonsense. Okay? And you'll know that, I think. Okay, so just put it in your calculator like this. In parentheses, negative 32 plus the square root of 2176, close parentheses, divide by -6. Okay, so that will be negative 2.44 seconds. That's nonsense. Okay, time can't be negative, right? And then we go negative 32 minus the square root of 2176, and then close parentheses, and then divide by -6. A much more sensible answer, I think. Okay, so that's about 13.1 seconds. Okay, so that should be the solution to that problem then, is that. Okay, so that's how I did that on the calculator. Okay, all right, so now let's move down. We're going to do a little bit more on this, and then we're going to try to verify all these results graphically. Okay, so the answer to this was 13.1 seconds is how long it's going to take that to reach the ground. And on something like Mars, there's such a thin atmosphere, so, hardly any resistance at all, that's pretty accurate. On Earth, it's more complicated because there's air resistance. Now, on Mars, there is winds and stuff like that, so that kind of complicates it a little bit more. Okay, so this says, with what velocity does the stone reach the ground? Well, you got to go back to the velocity function, which is negative 12t plus 64. So let's write that down. V of t was negative 12t plus 64. So we're finding the velocity, so that means really what we need to do is just find the velocity when it reaches the ground, and that happened at about 13.1 seconds. Okay, so we're going to plug this in, and then we'll just go to the calculator, and then we'll calculate that out, and that'll give you the velocity on that then. Okay, so I'll go negative 12 multiplied by 13.1, and then plus 64, and that will give about negative 93.2, and let's see, it will be feet per second. That's what the units in the problem said, so it's feet per second. All right, let me ask you a question. What is the significance of that negative? We have a negative velocity, so what does that mean? Yeah, we're going down, okay, and that's what we expect. We're going down towards Earth, or no, we're on Mars, so we're going down towards Mars, so that's the idea. Okay, all right, very good. Now what we're going to do is, what I like about this problem is we did all of this stuff without, really looking at it graphically, and then graphically should verify everything on this problem. So that's what you want to do when you do your homework, is do it like this, and then, gosh, check everything graphically. You'll understand this stuff better, too, if you do it that way. So what I'm going to have you do is we go to y equals, and we're going to put in the position function. So negative 6 t to the second, got to use x, of course, plus 64 times x, and then plus 192. And then we're going to think about a good viewing window on here. So you want to get that put in. Now for a window, notice that we reached the ground at 13.1 seconds. Okay, so that makes sense to go from 0 to maybe about 14. Okay, that's logical. The original height was 192. See, this is going to be a y-intercept. So we need to choose a y value that's bigger than 192. Let's just say something like 300. And then maybe scale this by, let's just scale it by 100. Okay, let me see what this looks like. Yeah, I need to go a little higher. Okay, so why don't we go to 500? Now see, that's how I do things. I reason and think through, then I adjust. Now if I graph, now I've got a nice picture that I like. We could even go 400 and it's even better. So I'm going to change that one more time. Like that, I'm going to settle on that viewing window. And then we're going to just kind of look at this graph. Now, and I'm going to have you, graph this in just a minute, but I'm going to show you how to check everything on here. Okay, so when you do your graph, this is kind of what I want you to do on here. Now, I'm going to just kind of use the graph from the calculator, but what I want you to put on your notes is more specifically just kind of label a couple of things, and then you can estimate what it looks like, okay? So here's the idea. These are the key things here. So this is 14 seconds out there. This was 400 feet. If you label those things, that's all good enough, okay? And then this thing right here was 192 feet. That's where the rock started. So what we did is we kind of threw it straight. We threw it straight up. So it went up for a while, and then it went down for a while. Okay, like that. Now what we're going to do on the calculator is we're going to check all this stuff, all right? So you can just kind of sketch that out like that if you want to, and that's good enough. And then we're going to put a couple other things on here. So first of all, remember let's kind of go through all these results that we came up with. So the first thing was, at what time does the stone reach its highest point? 5.3 seconds. We'll do this. Just trace at 5.3. Well, that's at the highest point. Okay, what was the highest point? 362.7. There it is right there, see? You can just trace, and you can visually tell that that's where it reached its highest point. Okay, like that. Okay? Then, the other thing we said was, when did the stone strike the ground? So trace at 13.1. Well, look at that. Okay, right now that's saying it's 0.74 feet above the ground, so we rounded that off, so that's right. Okay, so that you can just simply trace on those things and get this. So one other thing that you want to probably do on your graph that you're drawing is just this. Okay, so that was about 13.1 seconds when it hit the ground. And let's see, this right here was about 5.3 seconds when it reached the max height. Okay, so see, all that stuff we did is verifiable. All right, and then the other thing is, I want you to notice that in here, the velocity would be positive. When you get here, the velocity is 0, just for that instant in time. Then the velocity becomes negative. Okay, so that's what you want to know from that graph. And what that graph is doing is, this is two-dimensional motion. So actually what you're doing is you're just throwing the stone straight up, and it's coming back down to Earth. But this is representing your displacement from the beginning, from that cliff, over time. Okay, this is so that's what this is represented by then. Okay, go to the next page, and I'm going to let you try one problem like that. Okay, so go ahead and see what you can put together. Okay, so let's look over the answers you should have got, and then this will be the end of this part of the video. So the first one, the velocity is the first derivative. So you should have got negative 18t to the second plus 72t minus 54. And you're only supposed to look at this from 0 to 4 seconds. And so we got that. So that plug in the 1.5. So if you evaluate the velocity at 1.5, you'll get 13.5 seconds, okay, at that point in time. And then the acceleration is the second derivative. So you need to do the derivative of this to get the acceleration. So that would be negative 36t plus 72. And then the acceleration at 3 seconds, just plug in 3 there to get negative 36 times 3 plus 72. So that is negative 36, and let's see, what was miles per second squared. So remember, the units are distance per time squared. When is the velocity 0? Okay, algebra. You need to take the velocity, which is this, set it to 0, solve the equation. Now, if you did the quadratic formula, you should get the same answer. All of these numbers divide by 18. Now, you're best off to just take out a negative 18. And not just an 18, but a negative 18. That makes the factoring easier. So when I factor, I get this. So that means 3 seconds and 1 second is when the velocity is 0. Then the next question, when is the acceleration 0? Well, you take the acceleration function, negative 36t plus 72, set that to 0, solve the equation, you get 2 seconds. So that's when the acceleration's at 0. And then, when is the acceleration positive? Well, you solve an inequality. So I did this, and then notice on this, when I solve this, since I divided by a negative, that greater than has to switch to less than. So between 0 and 2 seconds, not just less than 2, because we can't have negative time, so between 0 and 2 seconds, that's when the acceleration's positive. Okay? So that's what's happening there. All right? So, and then we got the graph here that I'll talk about. And all this stuff's verifiable, kind of, that we did here. So the idea on this is we want to determine when the velocity is positive and negative. Well, we've already taken the velocity and solved it when it's 0. The velocity is 0 from 1 to 3. Now, I did a sign chart in here to kind of test this. You can also look at your graph and tell visually what's going on. Right now, the velocity is negative because you have a negative sloping tangent line. Hold on, somebody's trying to call me. Nobody? Need to get, okay, so let's see, we're in. All right, I had somebody about my vehicle warranty for like the millionth time trying to sell me something. Okay, so let's take a look at this then. So what I did is I did test points. What I was showing you is the velocity is negative here. Then the velocity becomes positive because the tangent line is sloping up. Then the velocity becomes negative because you're sloping down. All right, so you need to be real clear on that. Remember, the velocity is tangent lines. Negative sloping tangent line, positive sloping tangent line, 0 sloping tangent line, then negative. So the velocity is positive from 1 to 3. The velocity is negative from 0 to 1. And then 3, not to infinity. The problem said you're only supposed to consider 4. Okay, and that would have a bracket on there because this says less than or equal to 4. So that would technically go like that. Now what I did here is I just plugged in test points. This is how you can do this without graphing. Take a number less than 1, like say 0, plug into the factored form, and you get a negative number. That means the velocity is negative. Take a number between 1 and 3. I picked 2. Plug in. So go negative 18, 2 minus 3 times 2 minus 1. You get a positive. Therefore, you have a positive velocity and so forth. So that's the idea. The other thing I wanted to mention on this problem too is where is the acceleration positive? From 0 to 2. It's kind of hard to see on there unless you think about this. You are speeding up here. So from there to there, the slope of the tangent line is actually increasing. So what's happening is the slope of the tangent line is increasing, therefore the acceleration is positive. Okay, so that's what that means. Okay, so that'll end this up, and have fun with this. This is good stuff, all right? A lot of you might be interested in engineering and physics and stuff, so this will help you out. Then I'll get to the second point. Part of the video will be recorded separately.